So in the first part of the lesson, I'm going to pick up where I left off in Lesson 9. In that lesson, we were factoring by grouping. And I'm going to show you how you can use factoring by grouping to factor trinomials in addition to using guess and check. So we're going to start by just factoring some trinomials. And then I'm going to show you that we can use the same trick for factoring some multivariable polynomial expressions. So we're going to start by working a couple of problems and looking for some patterns so we can come up with an algorithm that will allow us to factor by grouping. So the first example is similar to some problems you probably worked after Lesson 9. X squared plus 5x plus 2x plus 10. I'm going to try to factor this by grouping. Well, the first two terms in this expression have a common factor of x. When I factor that out, I'm left behind with an x plus 5. The second two terms, the 2x plus 10, share a common factor of 2. When I factor that out, I leave behind a factor of x plus 5. Now I have two terms with a common binomial factor of x plus 5. And when I factor that out, I leave behind a factor of x plus 2. So I just factored x squared plus 5x plus 2x plus 10, and I got the product of binomials, x plus 5 times x plus 2. Well, notice that what we really just factored was x squared plus 7x plus 10. 5x plus 2x equals 7x. In Lesson 9, we factored this trinomial using a guess and check method. Well, let's think about what happened here. We rewrote the 7x using a 5x plus 2x. 5 plus 2 equals 7. But there's something else about 5 and 2. 5 times 2 equals 10. So we rewrote the linear term using factors of 10 that added to 7. Let's try this again. So let's factor x squared plus 5x plus 6 by grouping rather than guess and check. So the first thing I want to do is rewrite my 5x term, breaking it up into two terms so that I have 4 terms and I can factor by grouping. And what I'm going to be looking for are factors of 6 that add to 5. Pretty easy, 3 and 2. So I'm going to rewrite the linear term as plus 3x plus 2x plus 6. And I just want to double check to make sure that what I wrote, the two expressions, are indeed equal, and they are. Now I'm going to try to factor by grouping. So the first two terms share a common factor of x. That leaves behind a binomial factor of x plus 3. The second two terms share a common factor of 2. Once again, that leaves behind a binomial factor of x plus 3. Factoring that out, I have x plus 3 times x plus 2. I've taken a few extra steps to factor this trinomial, but I ended up factoring it into the product of binomials. Just a quick check using FOIL, x squared plus 2x plus 3x, there's my 5x, plus 6. It checks. Let's try it one more time. X squared minus 3x plus 5x minus 15. Let's start by factoring by grouping. Factoring out the common factor of x from the first two terms leaves behind a factor of x minus 3. Factoring out 5 from the last two terms leaves behind x minus 3. Just want to double check, make sure this is not just a happy coincidence. Using the distributive property, x squared minus 3x plus 5x minus 15, everything checks. Factoring out x minus 3 leaves behind x plus 5. Let's look at what we really did. Notice that we just factored x squared plus 2x minus 15. Negative 3x plus 5x, that's positive 2x. So we just factored this trinomial. Where did this 2 come from? Well, negative 3 plus 5 Those are integer factors of negative 15, which add to 2. So let's use this to factor one more trinomial of this form. X squared minus 8x minus 20. I want to split that linear term up, negative 8x, into two parts. I'm going to do that by looking for factors of negative 20, which add to negative 8. So what I'm going to do here is I'm just going to make a table. I know that I want my product to be negative 20. One integer should be positive, the other negative. And I want the sum to be negative 8. Since the sum is negative, the number that's larger in magnitude needs to be the negative number. So I have, let's see, 1 and negative 20, that won't work. 2 and negative 10, that will work. 2 plus negative 10 is negative 8. So I'm going to use this to rewrite the linear term. X squared plus 2x minus 10x minus 20. Now I'll factor by grouping. Pulling out a factor of x from the first two terms leaves behind x plus 2. Now I'm going to pull out a factor of negative 10 from the third and the fourth term, and that leaves behind an x plus 2. Now before I move to the next step, I just want to do a couple checks here. 2x minus 10x, that's indeed negative 8x, and using the distributive property here, x squared plus 2x minus 10x minus 20. Everything looks good. I also want to say one other thing before I do the last step. At this stage of the game, if I've done everything correctly, I will have this common binomial factor if I've chosen the appropriate pairs of factors. So if you don't end up with a common binomial factor, chances are there's a small arithmetic or algebra mistake somewhere. But let's just finish this off. Both terms have a common factor of x plus 2. When I factor that out, I leave behind x minus 10. A quick check using FOIL shows that the product of these binomials is indeed x squared minus 8x minus 20. Now some of you might have been thinking, I could have done this another way. Why did Anne write x squared plus 2x minus 10x minus 20? Couldn't she have written it another way? And I could have. Let's look and see how that would have worked. So x squared minus 8x minus 20, I could have written this as x squared minus 10x plus 2x minus 20. Let me clear away some of the stuff so we can see what we have here. And now in this situation, factoring out an x from the first two terms leaves behind x minus 10. Factoring out plus 2 from the second two terms leaves behind x minus 10. We end up with x minus 10 times x plus 2. When I did it with a different order, I ended up with x plus 2 times x minus 10. So the point is, as long as you have the correct integer factors, in this case negative 10 and positive 2, you can split up your linear term in two ways. Both situations you'll get the correct result. So now let's do a different example here. Now I have 6x squared plus 10x plus 3x plus 5. First thing I want to do is check for common factors because I see I have a coefficient of 6 with the x squared. So I don't see a common factor. So I'm going to try the same trick of factoring by grouping and see if I get anywhere. So 6x squared plus 10x plus 3x plus 5. I notice that the first two terms have a common factor of 2x. When I factor that out, I leave behind a 3x plus 5. Now look at what I have for my third and fourth term. I have 3x plus 5. Well, I can factor out a 1, and that leaves behind 3x plus 5. Just doing a check at this stage of the game, using the distributive property, 6x squared plus 10x plus 3x plus 5, everything looks good. I have that common binomial factor of 3x plus 5. That leaves behind 2x from the first term and 1 from the second term. So now look at what I've done. I've actually just factored the trinomial 6x squared plus 13x plus 5. 10x plus 3x, what I had here, is 13x. So let's think a little bit about this 10x and 3x. So 10 plus 3 is 13. But 10 times 3 isn't 5, which is the constant term in this trinomial. Well, 10 times 3 is 30. Do you see a 30 somewhere in this trinomial? Well, there is a 30. 6 times 5. So what we just found here are integer factors of 6 times 5, 30, which add to the coefficient of x, 13. That's the strategy we can use to factor binomials where the leading coefficient is not 1. Let's try that. So now let's factor 2x squared plus 11x plus 15 by grouping. So the first thing I'm going to look at is the product of the coefficient of x squared and the constant term. 2 times 15 is positive 30. And I want integer factors of 30, which add to 11. I'm going to be very thorough here and write down all the factors. 1 and 30, 2 and 15, 3 and 10. 4 doesn't divide into 30 evenly. 5 and 6. 6 goes into 30 evenly. But when I get to 6 and 5, I have a repeat. So just like with guess and check, I can stop. Looking at the sum, 31, 17, 13, 11, I'm going to work with a 5x and a 6x to rewrite my linear term. So 11x is equivalent to 6x plus 5x. Again, I could have written 2x squared plus 5x plus 6x plus 15. Either way will work. And now I'll factor by grouping. I can factor out the common factor of 2x from the first two terms, and that leaves behind an x plus 3. I can factor out the common factor of 5 from the last two terms, and that leaves behind a common factor of x plus 3. If you've done everything correctly, you should have a common binomial factor. In this case, I have a common factor of x plus 3, and when I factor that out, I leave behind a 2x plus 5. Just quickly using FOIL to check. 2x squared plus 5x plus 6x, there's my 11x, plus 15. The factorization worked. Let's do it again. 6x squared plus 11x minus 10. Looking at the product of 6 and negative 10, that's negative 60. I want integer factors of negative 60 that add to 11. Well, let's see. Negative 1, positive 60. That won't work. Negative 2, positive 30. That's not working. But notice that the number that's larger in magnitude is positive. That's what I'm going to need to get a positive 11. Negative 3, positive 20. That doesn't sum to 11. Negative 4, positive 15. There we go. That sums to 11. So I'm going to use a negative 4x and a positive 15x to rewrite the linear term in my trinomial. Now when I write down this step, I always check, make sure my signs are okay. 6x squared minus 4x plus 15, that's definitely positive 11x minus 10. Now I'll factor by grouping. The first two terms share a common factor of 2x. That leaves behind a 3x minus 2. The second two terms share a common factor of 5. That leaves behind a 3x minus 2. Again, I just do a quick check to make sure everything's okay on this line. Looking at it, I see everything looks pretty good. I have a common factor of 3x minus 2 to both of those two terms. I need a 2x to get back the first term on the previous line, and a 5 to get back the second term. So let's check using FOIL. 3x times 2x, 6x squared. 3x times 5, 15x, minus 4x, that's 11x, and the last term, negative 2 times 5, there's the minus 10. What we've developed here is a general strategy that will work for factoring all trinomials. First thing we want to do is find the product of a and c. A is the leading coefficient, c is the constant term. Then we're going to find a pair of integer factors that add to b, a pair of integer factors of this product, ac, that add to b. Then we're going to rewrite the linear term of the trinomial using these factors of a, c. And finally, we'll be able to factor by grouping. Now, if we have our product AC and we look at all possible pairs of integer factors and we don't find a pair of integer factors that add to b, what this means is that we have a trinomial that cannot be factored, a prime trinomial. Now, before we work a couple more examples, I just want to point something out. When a is 1, a times c is just c, the constant term. We could have used this method for a equals 1 as well, and we would just be looking at the constant term when we were looking for integer factors that add to b. So now we have 9x squared minus 15x plus 12. This stage of the game we're thinking, well, I can factor just about any trinomial. But we still need to look for common factors to the three terms before we start. I notice that I have a common factor of 3 in all three terms. I'm going to factor that out before I do any more work. So 9x squared minus 15x plus 12. Factoring out a 3 leaves behind 3x squared minus 5x plus 4. What's inside the parentheses is a trinomial I can factor by grouping. I'm going to be looking at factors of 12 that are going to add to negative 5. Where did I get the 12? The 12 is the product of 3 times 4. Negative 5 is the coefficient of x. Since I have a positive product and a negative sum, I need both of my factors to be negative integers. So, what are my possibilities? Negative 1, negative 12, that won't work. Negative 2, negative 6, that won't work. Negative 3, negative 4, that won't work. Negative 4, negative 3, just back to where I started. So the trinomial 3x squared minus 5x plus 4 is prime. So at this stage of the game, the original trinomial is completely factored. We're going to just finish with a couple of examples of factoring multivariable polynomial expressions. Same trick. We're going to start by trying to factor by grouping. So I have 3x squared plus 15xy minus 2xy minus 10y squared. Let's look closely at the pairs of terms. The first two terms, I have a common factor of 3x. In the second pair of terms, I have a common factor of negative 2y. So I'm going to try factoring by grouping. Pulling out 3x leaves behind x plus 5y. Working with the last two terms, pulling out a negative 2y leaves behind x plus 5y. Why did I change the sign? Because negative 2y times positive 5y is negative 10y squared. Now I have a common binomial factor of x plus 5y in both terms. Factoring that out, I need to multiply x plus 5y by 3x to get the first term in the previous expression, and negative 2y to get the second term in the previous expression. So I've just factored a fairly complicated looking expression into the product of binomials. But if I look at this expression a little bit more closely, notice that 15xy and negative 2xy are like terms. When we combine them, we get 13xy. Also notice that 13, 15 plus negative 2, 15 times negative 2 is negative 30, and 3 times negative 10 is negative 30. So this polynomial expression with two variables is very similar to some of the trinomials we were just factoring with just one variable. Let's see if we can use the same sort of pattern and algorithm to factor another one. So now we have 2x squared minus 7xy minus 30y squared. So I'm going to look at the coefficients of the x squared term and the y squared term. 2 times negative 30 is negative 60. And I want to see if I can find a pair of integer factors of negative 60 which add to negative 7. So I'm going to start thinking about integer factors of negative 60 that add to negative 7. Let's see. 1 and negative 60, that's certainly not going to work. 2 and negative 30, that won't work. 3 and negative 20, that's not going to work. 4 and negative 15, that's negative 11, that's not going to work. 5 and negative 12, there we go. 5 plus negative 12 is negative 7. Let's see if we can rewrite the xy term using 5 and negative 12 as coefficients. 2x squared plus 5xy minus 12xy minus 30y squared. Let's try to factor by grouping. The first two terms have a common factor of just x. Factoring that out leaves behind 2x plus 5y. If the technique's going to work, I'm hoping I'm going to leave behind a binomial factor of 2x plus 5y when I work with the next two terms. Next two terms, a common factor of negative 12xy minus 30y squared. Well, let's see. 12 and 30 both share a factor of 6. They also, the xy and the y squared, share a factor of y. So I'm going to pull out a negative 6y. That leaves behind 2x plus 5y. Want to double check my work here to make sure this just wasn't wishful thinking. 2x squared plus 5xy minus 12xy minus 30y squared. Everything looks good. Finally, factoring out that common binomial factor, 2x plus 5y leaves behind a factor of x from the first term and negative 6y from the second term. So with this, I'm going to turn it over to Candace, who's going to work a lot more practice problems factoring trinomials.
In this part of the lesson, I'm going to focus on factoring second-degree trinomials with a leading coefficient other than 1. Another way we can say that we're factoring second-degree trinomials with a leading coefficient other than 1 is to say we're factoring trinomials of the form ax squared plus bx plus c, where a does not equal 0 and a does not equal 1. Let's factor 5x squared plus 11x plus 2. Remember, the first step in any factoring problem is to factor out common factors. I don't see any common factors other than 1, so let's go ahead and start factoring. So let's go ahead and try to factor 5x squared plus 11x plus 2. Anne just showed you factoring expressions like this by grouping. Let's see if we can guess and check. I want to take 5x squared plus 11x plus 2 and break it into a product of two binomial factors. Well, there aren't too many ways I can get 5x squared. I'm going to make the first terms of my binomials 5x and x. Looking at the constant 2, there's not a whole lot of ways to make a product of 2 either. 2 and 1. However, it makes a difference here whether I put the 2 in the first binomial or the second. So I could put the 2 with the 5x and the 1 with the x, or I could put the 1 with the 5x and the 2 with the x. Well, let's see what happens in each of these cases. Looking at our first case, our inner terms, 2 times x, multiply to 2x. Our outer terms have a product of 5x. 2x plus 5x is 7x. We want our middle term to be 11x. What about our other choice? Our inner terms, 1 times x, give us 1x, and our outer terms have a product of 10x. 1x plus 10x is 11x, so it looks like this factors to 5x plus 1, x plus 2. I want to check just to be sure. So for my check, I just need to FOIL here. 5x plus 1 times x plus 2. Product of my first terms, 5x squared. Product of my outer terms, 10x. Product of my inner terms, x. And the product of my last terms is 2. This is 5x squared plus 11x plus 2. That's the binomial we started with, so my factorization checks. Now let's factor 2x squared plus 5x plus 2. We always want to remember the first step in any factoring problem is to factor out common factors. This is really easy to forget. Looking at my trinomial, the only common factor I see is 1. So let's go ahead and start factoring again. I'm going to try this by guess and check again. I'm factoring 2x squared plus 5x plus 2. So I can get 2x by making my first terms in my binomials 2x and x. Looking at my constant 2, well again, the only way I can get a positive 2 using two positive integers is 2 times 1. But again, it makes a difference which order I put these in. So I can put the 1 with the 2x and the 2 with the x, or I could put the 2 with the 2x and the 1 with the x. Let's look more carefully at the second choice. The second choice doesn't even make sense. Remember, we looked for common factors in the original trinomial, and we only found a common factor of 1. There were no other common factors. But look at the second choice. That first factor, 2x plus 2, those two terms have a common factor of 2. In fact, I could rewrite this as 2 times x plus 1, factoring 2x plus 2, times the factor of x plus 1 that was already there. So we know ahead of time this isn't going to work. If it did, we would have been able to factor a 2 out of that original trinomial. Let's see if our first choice works. When we look at our inner terms, 1 times x is 1x. When we look at our product of our outer terms, 2x times 2 is 4x. 1x plus 4x is 5x. This is good. I wanted 5x from my middle term. So it looks like our trinomial factors as 2x plus 1 times x plus 2. I've already checked the inner and outer terms in FOIL, so I'm just going to check the first and last terms to make sure this really does work. 2x times x gives me the 2x squared I'm looking for. 1 times 2 gives me the constant of 2 I was looking for. So it looks like my factorization checks. Now let's factor 2x squared plus 9x plus 3. Remember, the first step in any factoring problem is to factor out common factors. Does this trinomial have any common factors? Well, other than 1, I don't see any. So let's go ahead and start factoring. Let's try guess and check again. I still have 2x squared as my first term in this trinomial. So when I break this into two binomials, I'm thinking 2x and x again. That constant 3 at the end is prime. When I multiply 3 times 1, I'll get 3, but I can put the 3 either in the first or second set of parentheses. So I can try 2x plus 1 times x plus 3, or 2x plus 3 times x plus 1. Looking at my first choice here, the inner terms, 1 and x, multiply to 1x. The product of the outer terms, 2x and 3, is 6x. 1x plus 6x is 7x. Look at our trinomial. We're looking for 9x. Well, let's look at our other choice. The inner terms, 3 and x, multiply to 3x. The outer terms, 2x and 1, multiply to 2x. 3x plus 2x is 5x. I want 9x. Since I only had two choices here, it looks like I can't factor this trinomial over the integers. Do you remember what we call that? We have a prime polynomial. So the trinomial 2x squared plus 9x plus 3 is prime. Let's try factoring 3l squared plus 14l plus 8. Again, we always want to remember the first step in any factoring problem is to factor out common factors. You're probably going to get really sick of hearing me say that today, but it's something easy to forget. I forget that sometimes, and I've done a lot of factoring problems. 3l squared, 14l, and 8 only have a common factor of 1. So let's think about how we can factor this. I'm again going to think about guessing and checking here. 3l squared plus 14l plus 8, I'm going to try to break up as a product of two binomial factors. For my first terms, I'm going to use 3l and l. Now my constant 8 at the end, this isn't prime. 8 has more than just a pair of factors as the prime numbers in the previous examples did. I could get 8 by multiplying 1 and 8 together. And I can change the order in which those appear, so I could also look at 3l plus 8 times l plus 1. But I can also get 8 by multiplying 2 and 4 together. So I can look at 3l plus 2 and l plus 4, or 3l plus 4 and l plus 2. Looks like I've got 4 different choices here in my guess and check method. Let's look at the first one. 1 times l gives me l for my inner terms. 3l times 8 gives me 24l for the product of my outer terms. L plus 24l is 25l. What am I looking for? 14l. This doesn't work. What about that next choice? 8 times l gives me 8l for the product of my inner terms. 3l times 1 is 3l. My outer and inner terms add to 11l. I'm looking for 14l. Let's go to that next choice. 2 times l is 2l. 3l times 4 is 12l. So my outer and inner terms would add to 14l. That's what I wanted. So it looks like this polynomial factors to 3l plus 2 times l plus 4. Again, I just checked that the outer and inner terms add up to 14l. I do want to check to be sure that the first and last terms are actually 3l squared and 8. Product of my first terms, 3l times l, is indeed 3l squared. And the product of my last terms, 2 times 4, is indeed 8. So it looks like this factorization checks. Now let's factor 3l squared minus 5l minus 8. Again, remember the first step in any factoring problem is to factor out common factors. You always want to check your polynomial for common factors. 3l squared, negative 5l, and negative 8 only have a common factor of 1. So let's start factoring 3l squared minus 5l minus 8 as a product of two binomials. So I'm thinking about guessing and checking again here. I have 3l squared for the first term, same as the last problem. This time, instead of having a constant of 8, I have a constant of negative 8. So now I need to think about numbers, integers, that multiply to negative 8. Well, I can think of quite a few. Positive 1 and negative 8 work. I can change the 8 and the 1 around in the parentheses. But since we're looking for negative 8 here, and I have a positive integer and a negative integer, I can also change the way those signs appear. That gives me 2 more choices. Plus, I need to look at 2 and 4. 2 times 4 gives me 8. So I've got 3l plus 4 and l minus 2 as a choice. I can switch the 2 and 4 around and look at 3l plus 2 and l minus 4. And once again, I can change those signs around, which gives me 2 more choices. Look at all those choices up there. I don't know what you're thinking right now, but what's going through my mind is, yuck. I don't think I want to try all those things. Is there another way I could factor this polynomial? Well, remember what Anne just talked about? Factoring by grouping? Let's go ahead and try that. So I want to factor 3l squared minus 5l minus 8 by grouping. Now, what do we need to do to factor by grouping? We need to think about our product, AC, So we need to think about 3 times negative 8, which is negative 24. Here we're thinking about product. And we want a sum of the coefficient of the linear term, which is, in this case, negative 5. So I'm looking for a product of negative 24 and a sum of negative 5. Well, let's think about this. If I'm going to get negative 24 from my product, I need a positive integer and a negative integer. If I want my sum to be negative 5, the integer with the larger absolute value needs to be the negative integer. So let's think about factors of 24. In fact, factors of negative 24. Well, let's start with 1. 1 times negative 24 is negative 24, but that has a sum of negative 23. That's not going to work for me. 2 times negative 12 is negative 24. That has a sum of negative 10. That's also not going to work for me. 3 and negative 8 have a product of negative 24. Here's a sum of negative 5. That's what I wanted. So I'm going to break up that negative 5L as 3L minus 8L. So let's rewrite this trinomial as 3L squared plus 3L minus 8L, and then we had that constant minus 8. Remember, it doesn't make any difference whether I write plus 3L minus 8L or minus 8L plus 3L. This factoring by grouping should still work as long as I've chosen the correct integers. Grouping the first two terms, 3L squared and 3L, those have a common factor of 3L. If I factor out 3L, I leave behind L plus 1. The second two terms I can factor negative 8 out of. If I factor out negative 8, that leaves behind L plus 1. Let's just check here. 3L times L is 3L squared. 3L times 1 is 3L. Negative 8 times L is negative 8L. And finally, negative 8 times 1 is negative 8. So far, so good. I also see that I have a common binomial factor now of L plus 1. If I factor out L plus 1, I leave behind 3L from the first term and negative 8 from the second term. Let's quickly make sure this really works. We can just use FOIL here. L times 3L is 3L squared, minus 8L plus 3L, there's our minus 5L, positive 1 times negative 8, there's our constant of negative 8. Seems to work. Now let's factor 6x squared minus 9x minus 15. Remember, the first step in any factoring problem is to factor out common factors. I do actually see common factors in this trinomial. 6x squared, negative 9x, and negative 15 all have a 3 in common. So let's start by factoring out that common factor of 3. If I factor out a 3, I leave behind 2x squared minus 3x minus 5. Now let's see if we can factor 2x squared minus 3x minus 5. Well, thinking about factoring by grouping, I want a product of 2 times negative 5, which is negative 10, and I want a sum of negative 3, the coefficient of x. So let's see, what are some numbers I can multiply together to get negative 10? 1 and negative 10 will give me a sum of negative 9. 2 and negative 5, well, that gives me a sum of negative 3. That's what I wanted. So I'm going to break up negative 3x as 2x minus 5x. So I still need this 3. I factored that out. It's part of the original polynomial. But I'm going to rewrite what's in parentheses as 2x squared. That's staying the same. Minus 3x I'm going to write as plus 2x minus 5x. And there's my constant of minus 5 at the end. Now I need to focus on what's in parentheses because that's what I want to factor by grouping. Since I'm going to be doing some more factoring, I'm going to put square brackets here to differentiate from the parentheses I'm going to use inside the square brackets. Looking at the first two terms in the parentheses, 2x squared plus 2x, those two terms have 2x in common. If I factor out 2x, I leave behind x plus 1. Looking at the last two terms in parentheses, negative 5x minus 5, those have a 5 in common. I'm actually going to factor out negative 5, which is often helpful in factoring by grouping. If I factor out negative 5, I leave behind x plus 1. That's what I wanted, the same binomial factor I got from the first two terms. Let's make sure that really does work, though. 2x times x is 2x squared. 2x times 1 is 2x. Negative 5 times x is negative 5x. And negative 5 times 1 is negative 5. Looks good. So I've got this factor of 3, my greatest common factor I pulled out at the beginning. Inside the square brackets now I have a common binomial factor of x plus 1. When I factor that out, I leave behind 2x minus 5. Notice here, now we have all factors. Everything's being multiplied together. Those square brackets aren't really needed. I could have just written this as 3 times the quantity x plus 1 times the quantity 2x minus 5. There are a lot of steps in this problem. I actually want to do a detailed check that I write out. I don't think I want to do this one in my head. So let's check here by first multiplying the binomials together, the x plus 1 and the 2x minus 5. So I can't forget that factor of 3. X times 2x is 2x squared. X times negative 5 is negative 5x. 2x times 1 is 2x. And 1 times negative 5 is negative 5. So I have 3 times the quantity 2x squared minus 3x minus 5. Distributing the 3, I have 6x squared minus 9x minus 15. Is that the polynomial I started with? It is. This is good. My factorization checks. Now let's factor 3p squared minus 10p plus 7. Remember, the first step in factoring any problem is to factor out common factors. I don't see any common factors other than 1. You might be thinking now, should I guess and check, or should I use grouping? I've talked about both of these techniques. Well, there really aren't any shoulds. It's completely a choice. When a and c are both prime, in this case 3 and 7 are both prime numbers, there are only two possibilities, so I sometimes guess and check in this situation. Remember, prime numbers, we're talking about positive numbers, and we're looking at positive 3 and positive 7 in this problem. So let's guess and check. 3p squared minus 10p plus 7. So what are my choices? Well, I know for the first terms in my binomials, I'm going to use 3p and p. 7, well, I just have 1 times 7. So I'm going to try 3p plus 1 times p plus 7, and let's switch the 1 and 7 around. So I'm also going to try 3p plus 7 times p plus 1. In my first guess here, 1 times p gives me p, and 3p times 7 gives me 21p. P plus 21p is 22p. That sum is 22p. What do I want for my middle term? Negative 10p. I'm doing something wrong here. I'm not ever going to get negative 10p for my middle term if I'm using positive 1 and positive 7 as my constants. So let's go back and rethink about the guesses I made here. I wanted to have positive 7 for my constant, but I know I need a negative number for my middle term. So both of these integers need to be negative. So the only thing I'm going to change in my guesses here is to make both 7 and 1 negative. So now when I go to check this first guess, negative 1 times p is negative p. 3p times negative 7 is negative 21p. Negative p and negative 21p is negative 22p. Still not what I want. What about the second choice? In this guess, I have negative 7 times p is negative 7p, and 3p times negative 1 is negative 3p. Negative 7p plus negative 3p really is negative 10p. So it looks like the polynomial factors to 3p minus 7 times p minus 1. Let's do a quick check. I can FOIL this in my head. 3p times p is 3p squared. That's good. 3p times negative 1, there's our negative 3p. Negative 7 times p, there's our negative 7p. That adds to negative 10p. We checked that down here. And our constants, negative 7 times negative 1 is positive 7. So this factorization checks. This looks like the problem that I just did, 3p squared minus 10p plus 7. The reason I pulled this up again is I wanted to think about what would have happened if I had factored by grouping. Well, let's try that. 3p squared minus 10p plus 7. I made a choice to guess and check. Let's try grouping. If I factor by grouping, I'm looking for a product of 3 times 7, 21, and a sum of negative 10. Well, we've already discussed the fact that we're looking for a couple of negative integers that have a product of positive 21 so that they can add to negative 10. So we need two negative integers that have a product of positive 21 and a sum of negative 10. Well, I can come up with those pretty quickly off the top of my head. Negative 3 and negative 7. Those indeed have a sum of negative 10. So I'm going to break up negative 10p as negative 3p minus 7p. So this is 3p squared minus 3p minus 7p plus that constant of 7. From the first two terms, I can pull out a common factor of 3p. Pulling that out leaves behind p minus 1. From the second two terms, I can pull out 7 or negative 7. I want to pull out negative 7 here so that I can leave behind p minus 1. So now I have this common factor of p minus 1. When I factor that out, I leave behind 3p minus 7. So the same thing I got by guessing and checking. The only difference that you might notice here is that the factors are written in the opposite order. That doesn't make any difference. We can multiply in either order. Now let's factor 10p squared minus 5p plus 5. Good thing I have this reminder here. There is a common factor this time. 10p squared, negative 5p, and 5 have a common factor of 5. So if I pull out that common factor of 5, what do I leave behind? 2p squared minus p plus 1. Factoring out common factors first is mandatory anytime you're asked to factor a polynomial, but you can choose whether you want to factor by grouping or use the guess and check method. In the last example, I showed both ways. Let's think about how we want to do this one. Well, 2 is prime. 1 has only one choice of factors, 1 times 1. So I think guess and check is going to work here, because the only thing I have to try here is 2p and p for the first terms of my binomials, 1 and 1 for the second terms, although I do need to think about sign here. Looking at my middle term in the polynomial in parentheses, I have negative p. So what if I put in negative 1 and negative 1? This is actually my only choice. Does it work? Well, let's see. Negative 1 times p gives me negative p. 2p times negative 1 is negative 2p. When I add negative p and negative 2p, I get negative 3p. I wanted my middle term to be negative p. This was my only choice. It looks like, since I only had one choice and this choice doesn't work, that this equal sign that I just wrote down is not correct, and I want to do some erasing here. The polynomial 2p squared minus p plus 1 is prime. So the only factoring I can do on this original polynomial, 10p squared minus 5p plus 5, is to pull out that greatest common factor of 5, and I've already done that. Now let's factor 3j squared plus 4j plus 1. Do we see any common factors? 3j squared, 4j, and 1 don't have any common factors, so let's go ahead and think about factoring this into two binomials. Do I want to guess and check, or do I want to use factoring by grouping? Well, looking at that 3 and the 1 at the end there, I think guess and check's probably going to be pretty quick here. So for the first terms in my binomial, 3j and j, I want a positive 1 at the end. I want a positive 4 in the middle. Everything's positive, so let's put in plus 1, plus 1. And let's make sure that this being our only choice does work. Looking at our inner terms, 1 times j is j, and our outer terms, 3j times 1 is 3j. j plus 3j is indeed 4j, which is what I wanted for the middle term. Now checking the first terms, 3j times j is 3j squared. 1 times 1 is 1, which is what I wanted for the constant. So this factorization seems to work. Now let's factor 6a squared plus 5a minus 6. Remember, the first step in any factoring problem is to factor out common factors. I don't see any common factors other than 1. So let's go ahead and factor 6a squared plus 5a minus 6. Now again, I can choose to guess and check, or I can choose factoring by grouping. Since the coefficient of a squared is 6, which is not a prime number, I don't think I want to guess and check. To complicate matters even more, the constant at the end is negative, and we saw that that creates a lot more factors. Let's try factoring by grouping. So I want my product to be 6 times negative 6, that's negative 36, and I want my sum to be the coefficient of a, which is positive 5. So let's think. Can I think quickly of two numbers that I could multiply together to get negative 36 and add together to get 5? Well, thinking about my multiplication tables, 9 times 4 is 36, and if I make 9 positive and 4 negative, indeed, that adds to 5. So I'm going to break up that 5a as 9a minus 4a. So I have 6a squared plus 9a minus 4a minus that constant of 6. 9a minus 4a gives me the 5a. So far, so good. Now I want to look for common factors in my pairs of terms. Looking at the first two terms, 6a squared and 9a have a common factor of 3a. Factoring out 3a leaves behind 2a plus 3. Looking at the last two terms, negative 4a and negative 6, 4 and 6 have 2 in common. I want to pull out that negative as well. So I'm going to pull out negative 2, which leaves behind 2a plus 3. I have the same binomial factor. Let's make sure I really did factor these correctly. 3a times 2a, 6a squared. 3a times 3, 9a. Negative 2 times 2a is negative 4a. Negative 2 times positive 3 is negative 6. I haven't finished factoring, though, because I still have that subtraction between these two terms. I noticed already I have a common binomial factor of 2a plus 3. If I pull that out, I leave behind 3a minus 2. Let's make sure this works. 2a times 3a is 6a squared. 2a times negative 2 is negative 4a plus 9a. There's my 5a. And finally, 3 times negative 2 is negative 6. So this factorization works. Now let's factor 6k squared plus 17k plus 10. Do I have any common factors? Doesn't look like it. 17's prime. 6 is not prime. 10 is not prime. I don't want to attempt factoring by guess and check. So let's try factoring by grouping. 6k squared plus 17k plus 10. I'm looking for a product of 6 times 10, which is 60, and a sum of positive 17. That's the coefficient of k. Can I think of two numbers that when I multiply them together, I get positive 60, and when I add them together, I get 17? Well, again, if I think of my multiplication tables, 12 times 5 is 60, and 12 plus 5 is 17. So I'm going to break up 17k as 12k plus 5k. So we have 6k squared plus 12k plus 5k, that's my 17k, plus 10. Now I'm going to factor by grouping. The first two terms, 6k squared and 12k, have 6k in common. When I factor that out, I leave behind k plus 2. 5k and 10 have 5 in common. When I factor out a 5, I leave behind k plus 2. I have the same binomial factor in both terms. Let's make sure I did that correctly. 6k times k is 6k squared. 6k times 2 is 12k. 5 times k is 5k, and 5 times 2 is 10. So now pulling out that common binomial factor, k plus 2, I leave behind 6k plus 5. A quick check with FOIL in our head should confirm that this is correct. K times 6k is 6k squared. 5k plus 12k is the 17k, and 2 times 5 is 10. Now let's factor 5r squared plus 12r plus 8. Remember, the first step in any factoring problem is to factor out common factors. I don't see any common factors other than 1 in this problem. So let's go ahead and factor. Since 8 at the end there isn't prime, I'm thinking factoring by grouping again. So this time I want to find two integers that multiply to 5 times 8, which is 40, and add to 12. Can I think of two numbers that multiply to 40 and add to 12? Well, I'm not coming up with anything quickly, so let's make an organized list here. Of course, 1 and 40 multiply to 40, but that gives me a sum of 41, not 12. 2 and 20 have a product of 40. That sum, though, is 22. 3 doesn't go into 40. 4 and 10 multiply to 40. Those add to 14. I want 12. 5 and 8 multiply to 40. That sum is 13. 6 doesn't go into 40. 7 doesn't go into 40. 8 does. That gives me 8 and 5, but we've already looked at that. We're encountering repeats, so it's time to stop. Since we don't have any pair of positive integers that multiply to 40 and add to positive 12, it looks like this polynomial is prime. So the polynomial 5r squared plus 12r plus 8 is prime. Now I'm going to turn this over to Steve, who's going to talk about a whole bunch more factoring problems.